Hello everyone, welcome back to building a simple 6502 based computer on a breadboard. So last time in the first video, our focus was on the 6502 itself, on the CPU, which is this big chip there. So that should be working now, and everything here is pretty much in the same state that I left it in at the end of the last video. One thing I did try changing was to see if I could get it to run slower, because we had that problem where I could barely see the LED blinking even on the highest address bus line. I did try changing this 2 megahertz crystal for a 1 megahertz crystal, because I have a 1 megahertz crystal as well, and it just didn't work at all. It just, the CPU just stopped running entirely, so I don't know why. I don't know if that was too slow for it, or if the circuit here, if this clock circuit is somehow dependent on having a 2 megahertz crystal and it won't work with other crystal speeds. I don't know. Like I said, the circuit's a little bit magic, but it works, and I don't want to mess around with it too much. If I had an oscilloscope or something like that to analyze it with, I could understand it better, but I don't, so that's the end of that. So what are we going to do today? So last time we sent instructions to the CPU by way of these resistors here. We basically hardwired NOP instructions, no operation instructions, to the CPU, so it just keeps running that same instruction over and over. That's a good start when you want to test to make sure that the CPU is running at all, because then you can see it counting up through the address bus lines. If I had a logic analyzer, you could actually see the different address lines counting up from 0 to 65,000, whatever it is, whatever 2 to the power of 16 is. But I don't, so we just had to use the LED and kind of improvise with that. So that's fine. That's a good start. But what you really want to do when you have a CPU is you want to have some memory, because memory will contain the instructions that the CPU will run. There's kind of a debate about whether memory should separate instructions from data. I believe if I'm not mistaken, if I remember right, I think the Harvard model is sort of a computer architecture in which there are 2 memory stores. There's one for instructions and there's one for data. But most computers today use, if I'm not mistaken, the von Neumann model, which is basically there's just one memory space and instructions and data are mixed there together, and they're actually indistinguishable from each other if you don't know what format the memory data is in. So, okay, so we are going to have a memory chip, and that is this guy here. By the way, I am once again grounded, just in case anybody wonders. Yes, I did ground myself for this video. So this, okay, well, what you're seeing is mostly not the memory chip itself. This is actually a housing for it. Let me go ahead and open this up carefully. There we go. It opens up like that. And that little guy that you see in there, that is a ROM chip, or more specifically, an EEP-ROM. I can't quite clearly see. Actually, no, let me take it out for a second. I can take it out of this again carefully. I'll put that to the side for a second. So this here, I am grounded, but I still don't want to touch the pins, just because it's a good habit to form to not touch chip pins if you can help it. So you can see this is an Atmel chip. It's made by Atmel, which is, a company. It's a manufacturer of semiconductors. And the model of the chip is can you see that on the camera? You can kind of see it. I believe it's the 26C64B. Is that right? Yeah, it's the AT26C64B. I don't know what the numbers imply. 28 probably means that it has 28 pins, which it does. And the AT, I think, stands for Atmel, which is the manufacturer. But the rest, I don't know. So, most of you probably know, broadly speaking, there are 2 types of memory in computers. There's RAM and there's ROM. RAM is the main sort of address space. That's where the computer does its work. That's kind of the working area of the computer. ROM stands for read-only memory, which is so named because you can only read from it. You cannot write to ROM. It's hard-coded. It's not changeable. This chip here is technically an EEP-ROM, which stands for electronically erasable and programmable ROM. So it is a ROM chip in its normal everyday life, but it can be reprogrammed. There is a write pin on it. So let me see, where's the... Let me get the pin out for this chip just for a second. I think I printed it a little too large. It's going to have trouble fitting into the camera image, but okay. So this is the pinout of the chip. So you can see it's mostly the address bus and the data bus. So NC stands for not connected, so pin 1 is not connected to anything. This is the address bus here, and then I/O. This manufacturer calls these I/O pins. Other manufacturers may call them D pins for data pins. D stands for data, I/O stands for input-output, but in this case, they're equivalent. So D pins or I/O pins on these kinds of chips, it's the data bus. This is the ground pin, and here we have the rest of the data bus, and then a little bit more of the address bus, but here we also have 3 special VCC is just the positive power supply. But then there are 3 pins here which have an E on the end and a line over them. The line over them means that they're active low, which means they're active when the voltage is at 0 volts, and they're inactive when the voltage is high at 5 volts. And the pins are write enable, which is used to write a byte into the chip. So you use this if you want to write into the EEPROM. OE, output enable, which you turn on when you want the chip to output, so you don't want to write to it, you want to read from it, you want to read what's in that ROM. And then CE is chip enable. So if this is inactive, if CE is inactive, then the whole chip is turned off. It's kind of like an on-off switch. So that's pretty much it. You have the 3 enable pins, and that's actually it. You have the 3 enable pins, you have the 2 power pins, and the rest of it is just the address bus and data bus. That's the whole chip. A lot of these kinds of ROM chips use a very similar pinout. The ROM chip that I used about 20 years ago when I was building this project had a very similar pinout to this one. I think just 2 pins were swapped, if I remember right. I compared the 2 layouts, and I think just like almost everything is identical. There are just 2 pins, like I think 2 address bus pins, which were swapped with each other. Everything else was the same. So it's kind of I guess kind of like a de facto standard. Like most EEPROM chips have a similar layout to this, but still, do not rely on layouts like this unless you're sure it's exactly for the model of chip that you have, because this is, this model from Atmel. This diagram that I have is specifically for this model. Other ROM chips may have slightly different layouts or even completely different layouts, who knows. So make sure that the diagram you have is for your chip. So, yeah, EEPROMs are nice because you can program them, and I did program this one. So I actually programmed it manually, which is a very painstaking process. It's not something you want to do if you have a lot of bytes, but the program that I'm going to be running for this first test, or this first kind of project, if you will, only has, I think it has between 10 and 20 bytes in it. So you can manually program 10 to 20 bytes in, I think it took me something like an hour to do, which, again, it's kind of painstaking work. It's not something you'd want. If you have real programs, like real software that goes into the kilobytes, the thousands of bytes, forget it. You do not want to program that by hand. It'll take you days. That's ridiculous. For that, you want a chip programmer, which is an automated device that will, write to the chip. But if you have a very small test program like this, you can program it by hand. I don't have a chip programmer, so I didn't have much choice. I could have bought one, but I thought, no, I'll just do it by hand because the program is so small. And I'm not really planning to do much with this chip after the sequence of videos is over, so it would just be kind of a wasted purchase if I got a chip programmer for this. So one thing that you might also notice is this is not a DIP. So the other 2 chips that we saw are so-called DIP, dual inline package chips, which work great for breadboards like this because they have rows of pins that just go right into the holes on the breadboard. This is a so-called SOIC, small outline integrated circuit, and you can kind of see, I don't know how well it's showing up on the camera, it seems a little bit blurry on the camera. Basically this has gull wing leads, which are kind of like, I guess they're called gull wings because they look kind of like seagull wings, they kind of look like bird wings, kind of coming out of the chip like that. So these obviously do not go directly into a breadboard. I guess just thinking, theoretically you could bend the pins downward, but yeah, they're spaced too close together. They still wouldn't go into the breadboard. Yeah, it's not a good idea. So what I did, 20 years ago, you could still find DIP versions of chips like this pretty easily. But today they're really such a niche application. They're hard to find, and if you do find them, they're actually abnormally expensive because they're such a niche application. Whereas chips like this you can find pretty readily. I think this one costs like $5, if that. I think it might have even been less than that. So these kinds of chips are still reasonably findable online. I got this from Mouser again. But the problem with this then is it won't go into the breadboard. So that's what this is for. This is it's just socket. It's really nothing more than just a socket device built for 28-pin SOICs. So you put the SOIC here, you lay it nicely in the here, and you don't need to apply any pressure. This is like a ZIF or ZIF, zero insertion source. Zero insertion source. Yes, wonderful. Zero insertion force. It is a ZIF or ZIF, zero insertion force socket, which means you just put the chip in there and it just kind of sits on top there. You don't need to push it in. And then you close the lid. It snaps shut, or it's supposed to snap shut. Come on. You can push here a little bit to help it snap shut. And then that's it. And then you've got on the bottom, it interfaces to a kind of like a breakout board, which will then go into a breadboard. This is also a very niche device. This thing here, I think, costs like $30, which is quite expensive just for a for something like this, because it's not an active electronic device. It's literally just, a so-called mechanical. It's just a packaging change. But it's such a niche thing because you don't have many people working with stuff like this. So, low volume stuff like this tends to get really expensive. This particular one is actually from Adafruit, which is a company that specializes in selling things like this to hobbyists. I think that there is the part number. You can actually see, by the way, if you look at the pins, you can actually see they look hand soldered. There's there's like remnants of solder flux on them, which definitely makes it look like it's hand soldered. So these are actually hand soldered devices. They're such low volume that they don't run them on an assembly line. They just have somebody soldering these by hand with a soldering iron. But yeah, this particular one is from Adafruit. In fact, I think this is the box that it came in. I mean, it came from Mouser, but it was still sent from this box. You can see their URL is adafru.it. That's cute. So yeah, so it's that's their logo. So this is the box for it. I guess you'd probably order it directly from Adafruit's website, but I got it from Mouser because I was ordering other stuff from Mouser, so it was a convenient thing to buy that along with the other stuff. So yeah. So this is a ROM, and this computer will not have RAM in it. That sounds a little bit weird because for most computers, the RAM is very important. But for a simple test computer like this, we just want to run a test program. I'm not going to make a real functioning computer out of this that you can actually, do, serious applications with. The point of this is just to show you how to build a computer. And then if you want to make a real computer out of it, you can. You'll have all the parts to do so other than RAM. But I mean, RAM works very similarly to ROM. Basically, the pinouts for RAM chips, they have the same types of pins as ROM chips. So they'll usually have a chip enable and an output enable and a read-write pin or something like that. So the principles will be almost identical. It's just, a physically different chip. If you want a RAM chip, you'll need to get a physically different chip from this one. So you can put a RAM chip and a ROM chip into the computer, and then, have them both. But fundamentally speaking, basically all computers need ROM, because when the CPU first boots, it's going to look for a specific memory location. It's going to look in the memory for a specific memory address, and there has to be something there. There has to be something in that address in the memory. And when RAM first turns on, RAM is, it doesn't have anything in it, or it just has completely random bits and bytes. It's not actually anything meaningful. So you basically need ROM. Theoretically, you could build a computer without ROM, but without getting into any kind of, fancy exotic computers that do some weird fancy tricks, a basic computer standardly needs ROM because that's where the CPU boots from. When the CPU first turns on, it will read its first instructions from the ROM, from the read-only memory, from the instructions that are hard-coded into the ROM. So we will need a ROM to get the CPU to do something useful. So what I'm going to go ahead and do first of all is I'll take these 8 resistors out that I used to hardwire the NOP instructions. So here we go. 1, 2, 3. This one's a little stuck. This breadboard sometimes grips rather tightly onto things and it doesn't want to let them go. 3 resistors, 4, 5, 6, and I'll pull out the last 2 together. All right, there we go. So now we have the data bus, the data pins of the CPU, again, unconnected to anything. And we're going to go ahead and basically all we need to do with this ROM, well, the first thing you need to do with the ROM is program it. So I've already programmed this ROM, so it should be good to go. and then you need to connect it to the CPU. So the pinout is pretty straightforward. We're not going to write anything to this ROM after it's been programmed, so the write enable pin will stay high because it's active low. Remember, the line over it means it's active low, so when this line goes low, the ROM will write to itself. It will store something inside itself, and we don't want to do that. So we'll make sure that this stays high. So actually this pin and this pin will both stay high always while the CPU is running, because this is the positive power input, and this needs to stay positive as well so the ROM doesn't start writing to itself. So these two will stay high while the computer is running. That's not connected. I'll leave CE turned on because, actually no we won't. CE will be, sorry, that's my mistake. Actually, CE will be activated by something which we will talk about a bit later. And OE also, okay, so OE and CE we will use, I believe, but the rest of these pins just connect directly to the CPU. I mean, the CPU has 8 data pins, so these I/O pins just go directly to the CPU's data bus. And the address lines, this ROM chip has 13 address bus pins. Those go to the lower 13 address bus lines of the CPU. What do we do with that leaves 3 pins on the CPU, that leaves the 3 high pins of the CPU's address bus. What do we do with those? We'll talk about that later. But for now, let's see. Yeah, we just, let me go ahead and get this EEP ROM back into its little housing here. It's already been programmed. Like I said, I've programmed it, so we don't need to worry about that. I will just carefully put it back in. You can see, I don't know if you can quite see it, but in the top left there is a little circular indentation, which shows that that's pin 1. So we'll want to remember that that is pin 1 in the upper left corner there. Gently and carefully put it in place. It kind of slides around a bit. It's a little, it doesn't really push in. It actually, like if you look at it, you can kind of see it kind of slides. It's a little bit wonky because I'd like it to kind of push into place, but it really doesn't. It just kind of sits on top there, and then you carefully close this until it clicks shut. It didn't click because I closed it so gradually that it actually didn't click into place, but it did close. So there we go. So we've got our ROM chip back here inside this little housing, and I've been debating where to put this. The problem is, the wiring for this is going to look horrible because we're basically using almost all the pins on the left side here and most of the pins on the right side here. Most of those pins will need to connect to the CPU. And we're also going to be connecting them to both sides of the CPU. So basically both sides of this need to connect to both sides of this. So there's really no way to make it look nice and tidy. I mean, in an ideal situation, you could have a situation where like maybe all the pins that you needed to use for the CPU were on this side, like on the left side of the ROM, and all the CPU pins you needed were on the right side of the CPU. Then you could just put this here and just have wires bridging this gap here. But no, I mean, no matter where you put the ROM, it's going to look ugly because, again, both sides of this will need to connect to both sides of that. So it's kind of a no-win situation. So you know what, I'm just going to stick the ROM over here, kind of off to the side here, and push it into the breadboard like so. I mean, the reason I did that is just because nothing else needs to connect to the ROM. The only thing that the ROM needs to connect to is the CPU. We're going to have some other stuff here connecting to the CPU later. So I'll just put the ROM here. It's kind of an awkward place because it's sort of in the corner here, but that's okay because it doesn't need to connect to anything else except the CPU. So we just need to bring wires from here over to here. It's still going to look horrible, but and you know, I mean, I'm not that much focused on appearances. I mean, I'm not too worried about it looking pretty or looking neat and tidy, but we're going to have so many wires here that it's actually going to be hard to route them. We're going to have such thick and dense wiring, it's actually going to be difficult to route them to the right places. And also, this housing here, it's actually easier to do with a DIP ROM chip. The problem with this housing here is it's so tall. So the thing is, you can't just run a wire like from here directly over the CPU. It kind of has to go up. It has to go up and over the housing. So this is really going to get in the way. And in theory, this is actually really convenient because it lets you swap ROM chips. So if you want to change the firmware of the computer, if you want to swap out the the firmware chip for a different firmware chip, you could just pop this open, take the chip out, put another chip in, close the lid, and bam, you've done a firmware swap. In theory, that's really super convenient, actually. In practice, that advantage is somewhat offset by the fact that there are going to be wires over this, and there's probably not going to be room to easily just flip open the top and swap the chip out. It's probably going to be so cramped that we're not going to have room to do that. I don't know. We'll see. We'll see how it looks. See how it turns out. But I'm not hoping that it's going to look or be very very convenient or very very accessible. Okay. So actually, hold on. Let me go ahead and take care of the basic stuff here, and then I'll actually pause the camera, I think, because I actually put that in a kind of a bad spot, didn't I? Let me move this down just like one row down because that yellow wire there is, you can't really see where I'm pointing, but that yellow wire there, which connects to the CPU, is in the way, and I'll want that space to power up this ROM chip because the VCC, the positive power input, is in the upper right. So I'm going to move this just to like there. Is that going to be okay? Push that in, and I think we should be okay with that. Yeah, that should be okay. Okay, so let's go ahead and put in the wires that that we need, and actually, I'll need to get my wire tray. Hold on, actually, don't have it here with me. I'll be right back. Okay, nice little kind of tackle box of different wires for breadboards. So I will go ahead and open it up, put my ground strap back on because I took it off for a second to go and get the tray. All right, so what do we have here? So first we have positive voltage in the upper right. So I'm going to go ahead and take an orange wire like this and just stick that right there. Yep, that works. That should work fine. Okay, and yeah, I'm brushing against these resistors a bit, but that's okay. They're still in position, I think. Okay, so that's got it powered up now. That's the positive power input here. I'll put an identical wire right below it for write enable because we want to make sure that write enable stays high. I've already hand programmed this ROM and I don't want it to lose its programming. So it's a little inconvenient because if you look, you can see there's a gap in this bus here where I actually want to put that pin, but I can put it in the slot below it or in the hole below it. That should be fine. That should be reasonably doable. Yeah, when you have very dense wiring, breadboards are really not ideal. I mean, breadboards are good for prototyping if you want to do testing of circuits, but they're not. I mean, if you really want to do this properly, you should make like proper PCBs. But I mean that it gets really expensive to start manufacturing PCBs. So that's what I have here so far. So that's the power on pin on the left, and then the slightly angled orange wire is to keep write enable high so that the ROM does not store any information. Okay, and oh yeah, and ground is here in the lower left. So I guess yeah, let's go ahead and put a wire there and connect that to the negative side of the power supply so that stays low and the chip stays powered on. There we go. Okay, So negative goes in there, positive goes in there, and right enable stays high. So really, actually, all the rest of this ROM chip, the whole thing is just the address and the data bus, and then output enable and chip enable. So I'm going to talk a little bit later about what we do with output enable and chip enable, but actually, hold on. Let me quickly check. What did I do with those? Let me actually. I'm going to just quickly check what I did for that, because I honestly don't remember now that I think about it. I think, rather than assuming, let me look it up. The thing about this kind of thing too is a lot of ROMs today, like if you go looking for ROM chips or EEP ROM chips, a lot of them will be serial, which means instead of having a whole bunch, like a whole row of data pins like this, they'll just have one data pin, which makes them a lot easier to fit onto a board like this, because you don't need a bunch of wires. You don't need one wire for every bit. All the bits are transmitted on one wire. So physically, they're a lot easier to work with, but they're more difficult to program for and design for, because you have all the bits on one stream. Here, the bits are all separated. Every bit is on its own wire, whereas the serial ROM, you have all the bits together on the same stream, and it can be difficult to analyze if there's a problem with it. But let's see. Right, okay. Okay, so we are going to cover the OE and CE pins, the output enable and chip enable. We will cover those later on. So what I'm going to go ahead and do now is pause the video, and I'm going to wrestle with this for a while and try to get all those address bus pins and all those data bus pins connected to the CPU. It's just going to be a lot of wiring, and it's going to be really boring to watch. So I'm going to go ahead and pause the video for a while, and I'll go ahead and do that, and I'll catch up with you folks when that's done. So be back in a bit. Okay, we're back, and it looks like this. So yeah, again, obviously visually it doesn't look that great, but that's not really the big extent of the problems. Like I don't think this is the kind of thing that you'd really be doing if you care about things looking good, because obviously, maybe there's a certain sort of orthogonal aesthetic to it, but really this is something that you probably wouldn't be doing if you like things that look pretty. But yeah, the real problem here is just that when the wiring is this dense, and when things kind of crisscross over toward each other, it gets really difficult to actually get the wires into the right place. So I hope that I did that correctly. It's possible that I made a mistake somewhere. But I guess we'll find out. Yeah, this is really one of the most annoying parts of wiring up this computer. The ROM chip is actually probably the worst part of it, for two reasons. First of all, because you have to program it, and the programming takes so long. And then when you're actually wiring it up, there are so many wires here they have to put in. This is probably the worst part of the whole project. So, but hopefully the worst part is now mostly over. So we've got the ROM chip wired up and connected to all the address bus lines and the data bus lines. So again, what about those two enable pins? There's the chip enable and there's the output enable. Well, for those, we have another chip that we need to employ. I'm going to pull out, hold on, where is it? I think it's this. Is that it? Let me see. I think that's it. Where's the... There we go. Yeah. Okay. So again, I don't know how readable this will be on the camera, but this is a 74 LS. I think it's 138. Is that right? Yeah, 74LS138. You can see it at the bottom. You can kind of see it there at the bottom. As usual, my camera doesn't really want to focus on it properly, but that is what this is. So what is that? What is the 74138? Well, it's a 3 to 8 decoder, which I'm going to pull out the pinout for it, and maybe the pinout will help it make a little bit more sense. So it looks like this. So it's a fairly simple pin, for a simple chip. It takes, hold on. It takes 3 inputs from the address bus. These will be the 3 highest pins on the CPU's address bus. Remember, we're using a CPU here. The 6502 has a 16-bit, 16-pin address bus, so it can address 16 bits of memory. But the ROM that we're using here has only a 13-bit address bus. It does not use the 3 highest bits of the CPU. Instead, what happens is those 3 bits from the CPU go into this chip here. And excuse me, and with 3 bits, with 3 bits which can be either 1 or 0, how many possible combinations can you have? The answer is 2 to the power of 3, which happens to be 8. So yeah, with 3 bits, you can have 8 possible combinations. And if you look at the rest of this diagram, maybe it'll be a little bit more clear what that means to this chip, or what this chip is used for. This chip divides memory into 8 different segments. So if the first 3 bits of the address bus are off, then this pin becomes active, and you can address memory from byte 0 in memory all the way to byte 1FFF in memory. These numbers are all in hexadecimal, by the way. And then if the output of if the 3 highest bits of the address bus are 001, then this pin turns on, and then you can address memory from 2000 hexadecimal to 3FFF hexadecimal, and so on. So these are all on this side you have 7 outputs, and then on the left side there's 1 further output for the highest part of memory. Now the 6502 is going to look for a reset vector at the very top of memory. That's a little bit annoying because it basically means that you kind of have to put the ROM at the top of the memory. That's in marked contrast to the Z80 or Z80, which was another kind of competing microprocessor of the time. The Z80 or Z80 just starts executing instructions at 0. It just goes to 0 and starts running things from there. So potentially programming for the Z80 is a little bit simpler. With this chip, you kind of have to have everything at the top of memory. You don't really have a choice. Excuse me, sorry. So, yeah, so we will have to, because the CPU is going to look for a reset vector at the top of memory, we will need to put the ROM in this memory range, and this pin here will connect to the ROM. And you can see this pin is also active low, so guess what we're going to do with it? We're going to connect this pin to the chip enable and output enable of the ROM, because when we're looking for this memory range, we want to turn on that ROM chip. So really, we're not going to use any of these others right now. Later on, we're going to bring in one more chip, which will be in a different memory range, but we'll bring that in a separate video. So really, all the pins on the right-hand side here we won't use, except for the power input. So we'll connect positive power here, and then as again negative power goes in here. This will go to those 2 pins on the ROM. And, oh yeah, these 3 enable pins. You can use these pins to enable this chip, the 74138. These 2 are active low, as indicated by the line over them. This one's active high. But we can leave this always active. It's okay if this chip is always active. We don't need to turn it off for any reason, I don't think. So what we'll do, we'll connect the 3 highest address bits of the CPU to these 3 pins here. This pin will be tied low, and this will be tied low, and this will be tied high to keep this chip active. This will go to the ROM, and then just the 2 power pins. So the question is, where do I stick the decoder? I guess I'll stick it... Gosh. You might also wonder, obviously some of the distances here were shorter than others. I used all green wires because they're all the same length. I could have used some shorter wires for some of the shorter distances, but I wanted to use all the same length wires because apparently it actually makes a difference in terms of how far the signal, or in terms of how fast the signal travels from one pin to the next. So if you look at some old supercomputers from, back in the day, like I remember seeing an old Cray supercomputer at the Computer History Museum in Mountain View, California, and that computer is full of wires. It's just insane how many wires are just kind of bundled up inside it. And they could have made the wires a lot shorter, but the reason why those wires are all so long is because every path in that computer is the same length. They wanted every wire to be the same length because if you have, one long wire and then you have a short wire and they're both part of the same bus, well, the short wire is going to, transmit its signal first, and the bit on the long wire will get delayed somewhat because it has to go through that long wire. Electricity travels very fast. Actually, electricity travels at the speed of light, so that's super fast. But it takes about 1 microsecond, about 1 billionth of a second, for light to travel 1 meter. So, kind of like the distance between my two hands. Okay, maybe a little bit more than that. But, it takes about 1 millionth of a second for light to travel that distance. And a lot can happen with electricity in a millionth of a second. Wait, no, I think it might even be a billionth of a second. Sorry, I think it's nanoseconds, actually. I think it's 1 nanosecond that it takes light to travel a meter, so it's actually a billionth of a second. Yeah, I think that's right. Is that right? I think that's right. I think it's a billionth of a second. But a lot, excuse me, a lot can happen in 1 nanosecond. Really, you can have a lot happen with electricity. You have, a lot of these chips actually do internal switching at the nanosecond level. Like they'll have time limits of like 15 nanoseconds where they need to do things. So having signals arrive at different times makes a huge difference sometimes. This computer is not running that fast. Again, this CPU is just running at 1 megahertz. So maybe it's not that big of a deal for this one, but still, I wanted these wire paths to be all the same length. So that's why I used all the green wires. So I'm probably going to do the same for this chip here. I'm going to go ahead and put this chip, I guess, there, so it's kind of close to the CPU and the ROM, so it can kind of reach both of them. And yeah, it's actually good because the two enable pins are on the right. They're on the right-hand side of the ROM here, so having this chip on the right-hand side of the ROM is a good choice because it makes it relatively viable to get the wiring from this to the ROM to where it needs to be at the ROM. Thinking now. Okay, let's take this one step at a time. Okay, so in the lower left here we have ground. So let's go ahead and get that grounded. I will need, I believe, another orange wire. So, orange wire to the rescue. There it goes. Okay. And then in the upper right here, we have the positive power supply. So let's go ahead and get a another orange wire and wire up that side of the power supply. Okay, you can go there. Come on. There. Okay. Good. So now the chip's powered on. Actually, well, it's not powered on because I don't have power connected to the board, but it will get powered on when the board gets powered up. Okay, all the other pins on the right-hand side of this chip here we can ignore for now. We're going to use one of them for the I/O chip later, but that's for another video. So, what I do want to do is make sure that those enable pins are tied high. So 4 and 5 will want to be low. So let's go ahead and tie pins 4 and 5 to ground. So that's 4. Right? That is 4, isn't it? Yeah. Come on. There we go. So that's 4, and get another one for 5. Right next to it there. Cool. All right. And this yellow wire is in the way here. You know what? Rather than running a wire to the bus, let's just, oh, actually it needs to be a little bit shorter than that. Okay, I'll get a red wire. I'll get a short red wire. I mean, it doesn't really matter. It doesn't really matter, but I hardly have much use for these short red wires because they're too short to actually connect a chip to the power bus. So I might as well make use of them when I can, because, you know, red's a nice color. Red is the color of passion. There we go. Okay, so with this red wire here, I should be able to jump like so, theoretically. Come on, get in there. Wow. Oh, come on. The wire wants to go everywhere but into the hole. There we go. Okay. So I did that. So I connected that power pin directly to that enable pin, which is, I think, okay to do because, like I said, we'll want this chip to always be active. So positive power goes in, and oh wait, no, that's not positive power. Positive power is on the other side. Durr. Sorry. Okay, then I will need to. Oh, man, I should have checked that. Silly. Okay, never mind. Sorry, that's negative power, not positive power. All right. Then, well, that is a ground pin, so I will need to just do, actually, wait, no, a yellow wire, right? Let's do a yellow wire here then. So that is now, okay. Is that right? Let's make sure. Let me just double check all of this now. So ground is hooked up to ground, and E1 and E2 are tied low, and E3 is tied high. Okay. That is good. That is correct per the diagram. So E1 and E2 are tied low, E3 is tied high, ground is connected, VCC is connected. So what are we missing? We just need to run this to the ROM chip and these 3 to the CPU. So, okay, boy, I'm gonna get a couple of long wires again. The green ones are the longest in this wire kit. So we'll get 2 long wires. I could actually, on the ROM chip, I could have probably directly connected output enable to chip enable. That might have been a good thing to do, connect these 2 directly to each other. Can I still do that? Do I still have room to? I really don't. I really don't have room to do that, but I probably... Nah, I'll just... I should have done that before. I saved myself one wire run, but I think it's too late now. I can't really get a small wire, like a small little jumper wire between those two pins anymore. It's no room. So we want pin 7 of that decoder chip. I'm going to put 2 long green wires on it, like so. And I will run those to output enable and chip enable on the ROM chip. So give me just a second to do that. Well, it'll take more than a second. It'll take... Actually, I don't know how long it'll take because this horrible mess of wiring means that putting anything in there is less than ideal. So I have... Let's see... Where's the pin first of all? Which pin is it? It is that one. Yeah, it's that one there. Okay. So let's try to get the wire down there. If it's going to cooperate, and now it doesn't want to cooperate. It's actually okay. Wait, can I get the wire? Oh, maybe we can get the wire like so. Yeah, there we go. That seems to have worked. No, I just need to push. There we go. Okay, I got one of the 2 wires in. Now I need to get the other one in. That will go then. There. Okay, I see where it needs to go. It's just a matter of getting it. I apologize. I appreciate you can't see what I'm doing, but I'm holding the board in front of me because I need to see where the wire is going because it is just so hard to snake the wire in there. I really just couldn't do this if the board was lying on the table. Come on, get in there. Come on. Come on. There we go. Okay, I think I got it. Okay, so these 2 wires from that decoder chip now go to the ROM. Okay, so the ROM is now completely wired. All the address bus pins go to the CPU, all the data bus pins go to the CPU, OE and CE go to the decoder, and yeah, power is there and write enable is tied high. So I think we are done with the ROM. The ROM chip is done. And actually, do we need to, oh yeah, we need to do one more thing with the decoder chip. We need to run the 3 CPU lines to it. I think I can do that with shorter wires though, because the CPU address pins that we need are right here, and the decoder chip is right here. So actually, I can use some pretty short. You know what? Let me get 3 of the longer red wires. It's a red wire and another red wire, and yeah, I think we can do it just with these 3 red wires. Let's try that. So just make sure that that I'm doing this right. Yeah. Okay, let's go ahead and give this a try. So, all right, so pin 1 on the decoder chip here goes to the CPUs. You know, let me get this test wire out of here. I connected this test wire to the highest address bus pin, but we don't need it there now. I'm just going to put it there for a bit. So this will need to go to the 3rd highest CPU address bus pin, which I believe is... Looking at our diagram of the 6502 again, so this needs to go to A13, so it's the 3rd pin from that corner, so that actually just needs to go right there. That's not too bad. All right, another red wire. We put this on pin A1 of the 3 to 8 decoder. This will need to go to pin A14, so that's the 4th pin from the corner. So that just goes right there, like so, or no, not like so. Like so. There we go. Now it's in. All right. Last one. So this goes to right. So A3 on the decoder chip. Sorry, A2, because it starts numbering from 0. The 3rd address bus pin on the decoder chip goes to A15, which is the chip that we used with the LED before to test if the CPU is running. So that's the 5th chip from, or 5th pin from the corner. So it will go right there-ish. Yes, good. Okay. Well, I think with that we're done. We've wired up the ROM chip, we've wired up the decoder. So what I'm going to do now is I'm going to go ahead and turn on the power to this board. And let me just quickly make sure that I have power. I'm going to touch this test wire to the positive power rail. Yep, the LED turns on. It goes on, so I have power. And I'm going to reset the CPU with this reset switch. And if all goes well, if that program actually ran the way it should, so basically what happens when you reset the CPU is it goes straight to the ROM, and if all goes well, it should have actually run the program that's in the ROM. Now, how you troubleshoot at this point is totally dependent on the software. I'm not talking a lot about the software for this video because software is a big thing. Like really talking about the software would take a long time. Really, I mean, I should probably explain some about the software, but I'll probably do that in a future video. But for now, for this particular program, let me check. I believe yeah, so the CPU should be running in an infinite loop now. The program that I wrote goes through a few instructions and then it just gets in an infinite loop. So if things are running correctly now, A4 on this CPU should be stuck on. So A4 is that pin there. That's 1, 2, 3, 4, 5, 6, 7, 8. It's the 8th pin from the corner here. So if I go to the 8th pin from the corner here, am I going to see that it is stuck on? Actually, that's going to be, it's kind of hard to probe there because there's all this stuff in the way, but, gosh, which one is, I can't even see which pin is the 8th one from the corner. And you probably can't see it on the video or on the camera either. Oh, the LED, I accidentally touched something and the LED came on for a second. Hold on, let me see. Is this, okay, so A11 is off as it should be. A10 is on. That doesn't seem right. A10 shouldn't be on. Yeah, A10 definitely shouldn't be on, I don't think. Hold on, let me check. Yeah, that does not seem right. Oh dear. So I think at this point probably the worst thing that could happen is that I find I've got an error in my program, which is certainly possible when you hand program the ROM. Fortunately, I have enough space here. You can see the wires kind of arch over the ROM chip. So I have enough space here that I can actually extract this. I can actually pull this chip, pull this mounting or pull this housing off the board and kind of reprogram it or examine it if there's an error in the program. So all is not necessarily lost, but I was pretty careful when programming it, and I don't know why it would be, why there would be a mistake in it. And you know what I'm actually going to do? I'm actually going to go ahead and get a second wire because I want to kind of be able to come in from up here. So let me actually get another long green wire and I'm gonna try to get in from here. So I'll put that wire there, and I've got this as a probe wire that I can kind of stick on the CPU address bus pins there. Again, I can't see what the CPU is really doing. I mean, I can probe the data bus. I mean, we might as well. I guess we can do that. We can probe the data bus. So the first data bus pin is the 8th pin. 1, 2, 3, 4, 5, 6, 7. I mean, we can probe that. Okay, that's off. Okay, that's pulsing. So that's off and that's pulsing, or it was pulsing. Why did it stop? Interesting. So I think you can kind of see the LED flickering, but then it stops flickering, which it shouldn't do. I think that the behavior of the CPU might be a bit unstable for various reasons, but okay. Yeah, it's probably not good to directly probe the data bus like this anyway. It can kind of mess with the CPU. But okay, what I really want to do is probe the address bus pins. So pin 9 is the lowest address bus pin. That's this one here. Okay, it looks on, but I think it's just pulsing. I think it's not actually solid on. I think it's just pulsing. A2. Yeah, same thing. These are all going to be pulsing probably, but yeah. It definitely looks like it's doing something. Oh, that's interesting. It runs for a bit and then it stops here. So, or at least this one turns off. So what's the deal here? That is a 3. So it's the 4th bit. Aha. And that's actually correct, because after the program finishes running, that bit is not active. So it's on for a bit and then it goes off. So that's actually a good sign. What about the next one? The next one should be stuck on. It's not though. Okay, I feel like I might have a bug in the software. It doesn't really look like, it doesn't really look like it's doing what it should be doing, but at least it appears to be somehow reacting to the code from the ROM. So I think the worst thing that might happen at this point is that that I have either a problem with the software or maybe some kind of stability problem with the CPU. I'm not really convinced about the stability of the CPU overall. Something feels a bit fishy here. I mean, I guess what I could do, since, or actually, can I? I mean, I was going to say, I guess what I could do is like deploy this capacitor just in case it's power fluctuations on the power pins of the CPU. But first of all, I can't really do that because I don't have room. And secondly, I don't think that that's really the problem. I suspect that there's probably something else funny going on here. I wonder if okay, I'm not too convinced about what's going on here. I feel like something's wrong, but the good news is that at least the wiring here should be okay. So I'm going to go ahead and call this a success for the most part. I mean, it should be reading from the ROM. Next time when we actually start incorporating I/O, we'll actually see what it does. We'll actually see what happens. But for now, I think we're okay. I'm going to go ahead and I'm actually going to go ahead and take these test wires off because I think what I'll do after I stop filming is I'll try as a test, I'll put the I/O chip here and see if it gives the right outputs. And if it does, then the program's working. So I'll test that off camera. And then next time I will show you folks what the I/O chip is and how it looks and how it works. So I mean, fundamentally, this is a computer. I mean, it's a computer in the sense that it's got a program that's running now. So, you know, the ROM chip contains a program which is running on the CPU. So in that sense, it's a computer. What it's missing is a way to communicate with the outside world. So fundamentally, a computer, like the three basic building blocks of the computer are the CPU, which runs instructions, the memory, which stores instructions, and then I/O, which is a way for the computer to communicate with outside devices. So that's all we're missing now. We'll put that in next time. And if you want to add RAM to a computer like this, like I said, I'm not going to have RAM, but if you want to have RAM, you just need to pick one of these memory ranges to put it in, and then have it enabled from one of these outputs of the decoder chip, just like we did with the ROM. So the ROM is being enabled by this pin here, so you'll want to have your RAM enabled by one of these other pins here. And then that's pretty much it. Connect the address bus and data bus of the RAM chip to the CPU, just like I did with the ROM here. And the RAM should work the same way. It just needs to be in a different address range so that it doesn't get triggered when the ROM should be triggered, and vice versa. So I'm going to go ahead and call this a success because it seems to be working on some level. I feel like there might be a problem with the program, but again, if that's the case, then I can pull this out and try to inspect the program on it. That's reasonably doable. But the wiring here is done, and this is probably like the worst part of the project. So we should be in relatively clear skies now. So like I said, I'm going to go ahead and call this a success. I think the basic idea here is clear. And yeah, next time we'll work on that I/O chip and actually have the computer output something. So thanks for watching, everyone. Hope I'll see you next time. Until then, take care, everybody, and bye-bye for now.